Yeah, so today I want us to talk about linear expansivity. I remember last time we talked about the expansion. I even gave you I gave you the illustrations. Now, linear expansivity, we have two terms there. We have linear, which means in a straight line, and then we have expansivity, which means increase in length. So, linear expansivity basically means the expansion but along a straight line. Now, when you hit a particular material, like take for example, you hit a rod, the rod will increase in length. Now, that increase in length is known as linear expansion. The increase in length is known as linear expansion. But the tendency, how easy it is for a particular material to increase in length, that is what we call expansivity. So there's the term expansivity, which means the measure of tendency of a particular material to expand. That is what we call linear expansivity. So we have certain materials that expand more than others. For example, aluminium expands more than iron. That means if you take aluminium and iron and you heat them for a given duration of time, equal duration of time, there will be an increase in their sizes, but you'll realize that aluminium will increase more than iron. Now, in the table, we have a table here. I want us to look at this table. Now, in this table, we have the arrangement from aluminium all the way up to the invar. Now, these materials expand differently. Aluminium being the one that expands the most, and invar being the one that expands the least. You need to understand, or we need that knowledge on the linear expansivity for materials to be designed for particular uses. For example, if you look at aluminium is used to make things like the sufurias. Now, when you need aluminium for the sufurias, because sufurias are being exposed to large amounts of heat energy. Now, when they are exposed to these large amounts of heat energy, they need to be able to expand very fast so that the sufuria does not deform. If they were not able to expand very fast, then something will happen in that particular sufuria might crack. We take an example of steel. I want us to take an example of steel and invar. So look at this. We have steel and invar, these two. Now, steel will expand more within a short period of time compared to invar. Therefore, if these two are to be chosen for use, steel can be used to handle very high amounts of heat energy compared to invar. Because if invar is exposed to large amounts of heat energy, it will simply break because it does not have that uniform fast expansion, but steel will. Another example, I want us to take these two. I want us to take glass and Pyrex. Now, we have things like the test tubes. There are certain test tubes that are made from glass and others are made from Pyrex. Now, a test tube made from glass, if you take a hot liquid and you pour into it, or maybe use it for heating, if it is made from glass, there are high chances that it may crack. It will crack because glass does not have that uniform expansion, but Pyrex has a uniform expansion. So, when you consider the linear expansivity values, they can be used to decide on which material should be used for which particular type of work. So I think that is okay. Now, in building construction, we have beams. A beam is made from metals. Now, this beam needs to withstand very high amounts of pressure. So, a material will be chosen, steel. The material that is used to make a beam will be based on the expansivity value of this material. So, linear expansion basically is a very important aspect when it comes to thermal knowledge. You need to choose or a material will be chosen for a particular use because of its linear expansivity values. Now, another place where we can see the expansion is in the bimetallic strip. We have the bimetallic strip. Now, a bimetallic strip is a material. It is a material that is made from two metals reinforced together. Now, if you look at this diagram, I want to look at this diagram here. Now, in that diagram, we have one bimetallic strip. That bimetallic strip is made from brass. We have brass on the upper side, the shaded part, and we have iron on the lower side that is not shaded. So I want you to look at that diagram properly. Now, when this material is exposed to different temperatures, it will have different types of shapes. Now, take that we heat. Let's say we heat this material. Let's say we heat this material here. Now, if this material is exposed to high amounts of heat energy, brass expands more than iron. So if you expose this material to high amounts of heat energy, then brass will expand more. So if brass expands more, it will occupy the outer curve. So I want to look at that. The brass will be on the, so this will be the brass, and then iron will be on the inner side. Now the iron is on the inner side because it expands less. Brass expands more, so it will become longer. If it is longer, it's going to be on the outer curve. When it is cooled, brass will again cool more. It will contract more than iron. If brass contracts more than iron, then we are going to have a scenario where brass is going to be shorter. The shorter one is always represented on the inner side. So we expect in this case, when you are cooling it, that iron will be longer. Just a minute. Okay, iron will now tend to be longer, so it will take the outer curve. But brass will be shorter, then it will be taking the inner curve. So the two illustrations given here, the two illustrations that we've been given, the first one is when it is heated, and the second one is when it is cooled. So I need you to get that properly. If you're having any questions, you can just channel those questions. They will be answered. So there's a brief note given here. There's a brief note given in this point. Now that brief note tells us that when you heat a bimetallic strip, brass expands more than iron. I've said that. So when it expands more, it becomes longer. That is why it ends up forming the outer curve. The iron that is shorter will take the inner curve in a case of heating. When you do it the other way around, when you start cooling, the brass will contract more than iron. Therefore, iron becomes longer than brass. In that particular case, iron will be on the outer, will form the outer curve. This application is also, so we have various applications. One of them is in the railway lines. We have the railway lines. Railway lines use this idea of expansion. Now we have an example here. Now this is how railway lines have been made. I want you to, let's look at this. This is how railway lines are made. Now if you look at the two, we have two rails. There's one rail here and there's another rail here. Now between these rails there's a gap. I want to look at the gap there. There's a gap. Now this gap is very important because it allows the space for expansion. Now when this rail expands in this direction and this rail also expands in this direction, they cannot meet because there's an allowance created by that gap. So if they were meeting, then we expect a case whereby if let's say that is a rail and this is a rail, and then they meet, let's say they meet during expansion, they will exert pressure on each other. We expect it will bend. We expect something like that. But now that is where this gap comes in. that gap gives them an allowance. We call it an expansion allowance. So during hot periods, as the rails expand on both sides, they can only expand up to a maximum that they do not meet. They'll be very close to each other, but they don't meet. And when it is cold, they will contract. Now, the contraction is facilitated by the bolt holes. Now, we are having a bolt hole. I want to look at this demonstration. We are having, that is our bolt hole. So when a bolt is tied at this point, when we have a bolt at this point, then it gives a room. This can contract in this direction, and this can also contract in this direction. So there will always be a space. There will always be a space when the contraction is happening and when the expansion is also happening. So railway lines are made with gaps between them. These gaps between them allow for room for expansion to take place. They are also made with the bolt holes. The bolt holes are also helping in case of contraction or expansion, so that unnecessary pressure is not exerted on the rails. We also have certain rails that have been made, they don't have holes. Like if you look at this example, those rails do not have those holes, but they've been made in such a way that they overlap. Look at this region here, they overlap. So when they expand, they fit into each other. And when they contract, there's a space that is created between them. What is important still is there is no unnecessary pressure that they exert on each other.